So today I'm going to study the UniswapV3 things. I'm not sure how long I will stay here, but probably for some time. And my goal is going to be to first understand exactly how it works. I think I clarified a lot off stream of the things I didn't know or I was uncertain about. And now it's just a matter or more of really understanding how arbitrage works, the formulas, and the different types of arbitrages and how to put that into code, which just seems fairly simple, but it's actually really bit very confusing, can be very confusing with all the fees and the slippage. So the main thing I have in mind is trying to clarify that part for me because on the concept side is very simple. You have one coin, then you buy that, you make a trade. So let's say you have USDT, you trade for Ethereum, then you pick the Ethereum and you trade for another coin, and then from the other coin, you sell back to Ethereum. And that's the triangular arbitrage. And it's very simple, but the problem are one, the fees, two, the slippage, and three, how do you translate that into coding format for any specific a pair of coins, different pairs of coins, and how do you calculate the amount? I think that's the biggest problem for me, because as far as I understand right now, slippage is pretty much the rate. You take the rate of the exchange, which is the proportion of the coin based on the liquidity pool algorithm, and that's gonna be how much your order is gonna affect the price of the coin. So as you buy more and more, kind of like the same thing that happens on the order book, where you're not gonna be able to buy, for example, $1 million position just from one person usually. So you're gonna end up paying a higher price the bigger your order is, and that is slippage. And in the case of tax, it follows the rate formula, and then the amount is really gonna depend how much the price deviates. And that's the tricky part, because then if you're doing the triangular arbitrage, how you're gonna know how much you can trade initially, how to maximize and get the optimal amount that you need in order to fulfill the necessity of the market, let's say, the space for profit. Because as you buy and you sell, it's gonna reach the equilibrium. And that's really, I understand it on the concept level, but it's really confusing for me to think about it on how to translate that into code. So that's the main thing. The other main thing is figuring out the formula for UniswapV3, which UniswapV1 I already understand, is just the linear format, but UniswapV3 I think is different. So that's my main priority here, I think. So let me put this.
Concentrate.
Maybe I should talk more about it, because talking helps me clarify what I'm trying to do and how I should think about it. Yeah, so my idea is I'm gonna do this for a bunch of DEXs, and I wanna figure out how to get the data for all of them and these formulas. And then I'm trying to think about what's the best way, best logic to connect everything. I think it's very unlikely to make money. Maybe I'll make some money, but very unlikely, because it's super competitive. But I think it's something that is worth doing, because it translates into other areas, and not, you can think about it, you can take this and also combined with machine learning, and then you can start creating a bunch of projects out of that. So it's not just the arbitrage thing that is interesting to me about this. I think it's something I can grow more and more as I build this stuff. And for the Ethereum transactions and block information, I'm at about 900,000 now blocks. And I think in total there's around 14 million or 15 million. So it's going to take me probably around 40 days to get all the information. And I don't think I'm going to do it in a row. I'm going to give breaks in between. So it's probably going to take me more than that.
Behind V3. When LPs provide liquidity to a V2 pool, liquidity is distributed evenly.
But now it's a lot more clear to me. It's a lot simpler than I thought it was. The first time I think I was overcomplicating the way that it works. Oh, and the thing about the token, the way that it works as a liquidity provider, you just provide the pair amount. You can't put just one coin, you put both coins. And that ratio is the percentage of entitlement, let's say. It's kind of like purchasing a stock. You're buying into the fund. And when you withdraw, you get the same amount. And that, I had the feeling and intuition that that would be a problem. And it is a risk, they say, about doing this, which is called impermanent loss. Which is obviously that when people trade the money, you can't control the amount of coins you have. You are entitled to the pair itself, but you can't control the rate. But the more volume the coins have, the rates tend to go achieve an equilibrium because of the arbitrage thing. But if they don't, then you run the risk of if withdrawing the coin that is withdrawing a bigger amount of the coin that is worth less than the one that is worth more, and then you would lose money, and you have to compare that with just placing the money on the coins themselves separately, and seeing if that would make sense as a liquidity provider. But that's not my goal, so I don't really care about that. The final idea of UniswapV3 is considered liquidity. Liquidity that is allocated within a constant price range. In earlier versions, liquidity was distributed uniformly along the price curve between 0 and infinity. The previously uniform distribution allowed trading across the entire price interval, without any loss of liquidity. However, in many pools, the majority of the liquidity was never used. Consider stablecoin pairs. Okay, I went through the part. So basically, you can select the range in which your assets are active and the range that they are not. As the price of an asset rises or falls, it may exit the price bounds that LPs have set in a position. When the price exits a position's interval, the position's liquidity is no longer active and no longer earn fees. As price moves in one direction, LP gain more of the one asset as swappers demand the other, until their entire liquidity consists of only one asset. In V2, we don't typically see this behavior because LPs rarely reach the upper or lower bound of the price of two assets. If the price ever re-enters the interval, the liquidity becomes active again. In range, LP begin earning fees once more. Importantly, LPs are free to create as many positions as they see fit, each with its own price interval. Constrained liquidity serves as a mechanism to let the market decide what a sensible distribution of liquidity is. As rational LPs are incentivized to constrain their liquidity while ensuring that their liquidity remains active. So another thing that I just thought about that I should think while I'm studying this is how to correlate the formula of the rates with the swapping thing. That's the main thing that I have doubts on, because it involves the amount and the way that it's going to change the price of the coins. So I think I have to see formula, what smart contracts, what is allowed to get from contracts when it comes to price of tokens. So I want to understand if it's possible to get the price of each token from the contracts, or if it's only possible to get the amount of reserves, or both. Because if I only can get the amount of reserves, that's one way that I think I'm gonna think about it, the logic. And if I can get the price of a specific tokens, which I think is possible, then I think is another way of looking at it. Because I know intuitively that there is a very large advantage, not intuitively, also consciously, let's say, of having the formula of the rate, because what determines the price in the normal markets, the relationship between coins is going to be far more complex because it involves the infinity, like every other physical concept in relationship to each other, the way that people are connected, technology, etc. And in the difference in indexes is that it's programmatically, so you can predict. It's a lot far easier to predict the price movement if you can see the amount of orders coming and the amount of orders coming out. So I think that's the most interesting way to think about it. And I think that's only possible if I can get the price of the tokens, and the reserve amount, because then I have I can run the data analysis on the fluctuation of reserves and the flow of the coins between dexes. And that's the next step that I'm thinking about. After I build all of the stuff, create a circuit that allows me to gain data from all these places and then run data analysis on them to see if I can extract, based on not only this but on physical principles, I can extract some patterns of the way that people are behaving and the money is flowing, and then I can try to build stuff on top of that. I think that would be very interesting. To achieve concentrated liquidity, the once continuous spectrum of price space has been partitioned with ticks. Ticks are the boundaries between discrete areas in price space. Ticks are spaced such that an increase or decrease of one tick represents 0.01%, 1 basis point. Increase or decrease in price at any point in price space. Ticks function as boundaries for liquidity positions. When a position is created, the provider must choose the lower and upper tick that will represent the position's borders. As the spot price changes during swapping, the pool contract will continuously exchange the outbound asset for the inbound, progressively using all the liquidity available within the current tick interval until the next tick is reached. Tick interval refers to the area of price space between two nearest ticks. At this point, the contract switches to a new tick and activates any dormant liquidity within a position that has a boundary at the newly active tick. While each pool has the same number of underlying ticks, in practice, only a portion of them are able to serve as active ticks. Due to the nature of the V3 smart contracts, tick spacing is directly correlated to the swap fee. Lower fee tiers allow closer, potentially active ticks, and higher fees allows a relatively wider spacing of potential active ticks. While inactive ticks have no impact on transaction costs during swaps. Crossing an inactive tick does increase the cost of the transaction in which it is crossed, as the tick crossing will activate the liquidity within any new positions using the given tick as a border. In areas where capital efficiency is paramount, such as stablecoin pairs, narrower tick spacing increases the granularity of liquidity provisioning and will likely lower price impacts when swapping. The result being significantly improved prices for stablecoin swaps. For more information, fee levels, I'm gonna read the white paper next, and I also have this paper here, which is another paper I got from somewhere else. I think Bert Similar mentioned this in one of his videos, and then I downloaded the paper. I think I'm gonna read this. And the good thing about this is that it contains the actual formulas, so it's gonna be easier to translate that into code because I don't have to think about it. Just get the variables and put on the function. Obviously, I'm gonna understand what I'm putting on the function first, so I'm able to use it. But it's a lot easier than having to think about the structure of the thing. Because I couldn't find any good arbitrage models, triangular arbitrage models or formulas, only the explanation. But it's a little bit confusing when you're thinking about buying and selling things and the price difference. So it's a little bit annoying to do it. And I'm probably gonna make mistakes, obviously, and the first time that I do this. So I guess we'll just do it and see and correct along the way. Swap fees are distributed pro rata, showing range liquidity at the time of the swap. If the spot price moves out of position range, the given liquidity is no longer active and does not generate any fees. If the spot price reverses and re-enters the position's range, the position's liquidity becomes active again and will generate fees. Swap fees are not automatically reinvested as they were in the previous versions of Uniswap. Instead, they are collected separately from the pool and must be manually redeemed when the owner wishes to collect the fees. Pool fees tiers. UniswapV3 introduces multiple pools for each token pair, each with a different swapping fee. Liquidity providers may initially create pools at three fee levels: 0.05%, 0.3%, and 1%. More fee levels may be added by uni governance. The 0.01% fee level added by this governance proposal in November 2021 as executed here. Breaking pairs into separate pools was previously untenable due to the issue of liquidity fragmentation. Any incentive alignments achieved by more fee optionality invariably resulted in a net loss to traders due to lower pairwise liquidity and the resulting increase in price impact upon swapping. The swapping. I keep saying this wrong. The introduction of concentrated liquidity decouples total liquidity from price impact. With price impact concerns out of the way, breaking pairs into multiple pools becomes a feasible approach to improve the functionality of a pool for assets previously under reserved by the 0.3% swap fee. Yeah, so this makes things a lot more complicated as well. Because now I have to think about how I'm gonna put this into a function depending. I guess I just put it as an argument and they're probably gonna have functions to get this fee amount, I assume. Finding the right pool fee. We anticipate that certain types of assets will gravitate towards specific fee tiers based on where the incentives for both swappers and liquidity providers come nearest to alignment. We expect low volatility assets, stablecoins will likely congregate in the lowest fee tier, as the price risk for liquidity providers holding these assets is very low, and those swapping will be motivated to pursue an execution price closest to 1-1 as they can get. Similarly, we anticipate more exotic assets or those traded rarely will naturally gravitate towards a higher fee. So yeah, obviously more risk, higher fees, less risk, lower fees. UniswapV3 has a protocol fee that can be turned on by Uni governance. Compared to V2, Uni governance has more flexibility in choosing the fraction of swap fees that go to the protocol. For detail regarding the protocol fees, see the white paper. Automated market maker, smart contracts, assets. Digital assets can take many forms. Supports ERC20 token pairs and represents position in the form of an NFT. Liquidity that is allocated within a determined price range. Constant product formula. Market making algorithm is by Uniswap in V1 and V2. This was. Yeah, so now it's gonna be different than this formula. Smart contracts that are considered functional and are essential to swap. So uses ERC20. The factory smart contract deploys any smart contract for any pair. Flash swap trade that uses the tokens purchased before paying for them. Invariant, the key value, the constant. Liquidity, mid price, the price between the available buy and sell prices. This is the ratio of the true ERC20 token reserves. In V3, this is the ratio of the true ERC20 token reserves available within the current active tick. Observation, an instance of historical price and liquidity data of a given pair. So as I understand, this ratio, it changes with the slippage. So the ratio itself doesn't, yeah. I remember seeing that a video or somebody said that the graph goes up as you buy. So it changes the ratio, but I'm not really sure about that now that I think about it. Because the price of the true tokens definitely change based on the trading on that ratio, given the ratio. But I'm not sure if the ratio itself changes with the trades. I guess it does, so people are not incentivized to make very large trades because that would make the liquidity go towards zero or infinity. But I guess that's already calculated on the ratio itself. So I'm not sure about that. I have to think about more. An instance of liquidity defined by upper and lower tick and the amount of liquidity contained therein. Price impact, the difference between the mid price and the execution price of a trade. Protocol fees that are rewarded to the protocol itself rather than to liquidity providers. Range order, an approximation of a limit order in which a single asset is provided as liquidity across specified range and is continuously swapped to the destination address as the spot price crosses the range. Reserves the liquidity available within a pair were commonly referenced before constrained liquidity was introduced. Slippage, the price moves in a trading pair between when a transaction is submitted and when it's executed. I guess slippage doesn't change the ratio. It's just the lag between the volatility and the execution of the order and the amount of prices within the block. Spot price, the current price of a token relative to another within a given pair. Swap fees, the fees collected upon swapping, which are rewarded to liquidity providers. Taking it wrong. Okay. Unfamiliar with the concept of an oracle, check out the Ethereum's Foundation Oracles overview first. All UniswapV3 pools can serve as oracles, offering access to historical price and liquidity data. This capability unlocks a wide range of on-chain use cases. Historical data is stored as an array of observations. At first, each pool tracks only a single observation, overriding it as a block elapses. This limits how far into the past users may access data. However, any party willing to pay the transaction fees may increase the number of tracked observations up to a maximum of 65,000, expanding the period of data availability to 9 days or more. Storing price and liquidity history directly in the pool contract substantially reduces the potential for logical errors on the part of the calling contract, and reduces integration costs by eliminating the need to store historical values. Additionally, the V3 oracle's considerable maximum length makes oracle price manipulation significantly more difficult, as the calling contract may cheaply construct a time-weighted average over any arbitrary range inside of or fully encompassing the length of the oracle array. this is something I also still have questions about, which is the difference between, because some of these dexes allow borrowing and lending, and some of them don't, and it's very hard to figure out which ones do and which ones don't. So that's something that I'm not really sure about, if all the dexes are also automated market makers or vice versa, and what's the relationship between that? Because all of them work based on this principle of liquidity, providing liquidity, and but not all of them, I think, allow people to borrow from that liquidity as well as make transactions out of it. So I only found eight and maybe two more, I think, that I know that is explicit that they do offer, but the other, couldn't find many other ones. And that's also something I have to think about. Starting price and liquidity history directly in the pool contract substantially reduces the potential launch. Observations take the following form. Observations may be retrieved via the observations method on V3 pools. However, this is not recommended which consume Oracle data. Instead, prefer observe. Each time observe is called, the caller must specify an array containing any number of seconds ago, denoting the times to return observations from. Note that each of the given times must be more recent, or as old as the oldest stored observation. If the times don't correspond exactly to a block in which an observation was written, a counterfactual observation will be constructed, removing the need for the caller to interpolate manually. This is one of the primary reasons to use observe over observations. Note that because the oracle is only updated at most once every block, calling observe with a seconds ago value of 0 will return the most recently written observation, which can only be as recent as the beginning of the current block, or older. Yeah, because for obvious reasons. But yeah, the issue here is that I'm not sure if you can only call this with the smart contracts or if you can do it with Web3. So code, do like this so it's easier to read. I guess, yeah, you can make an abstraction of the contract and then call the function. So I'm just gonna put it in comments so that I don't get these annoying errors. And I think my idea is gonna be to use Node.js to deploy the contracts, which is easier, but then use everything else with Python because Python is more effective for data analysis, I think. I don't think there is maybe there are, but I don't know them. Methods for reading or writing to CSV files in JavaScript or manipulating this data. On Python, I'm a lot more used to doing that. Each time observes call, the caller must specify an array containing. Okay. As Oracle is only tick accumulator. The tick accumulator stores the cumulative sum of the active tick at the time of the observation. The tick accumulator value increases monotonically and grows by the value of the current tick per second. To derive the arithmetic mean tick over an interval, the caller needs to retrieve two observations, one after the other. Take the delta of the two values and divide by the time elapsed between them. Calculating a swap from the tick accumulator is also covered in the white paper, which is the thing that I'm gonna read next. Yeah, and this is interesting to put in the formula. I think is very useful, I think. Because it is the whole thing I was talking about earlier of figuring out the flow of the money. Using an arithmetic mean tick to derive a price corresponds to a geometric mean price. Our code library for an example of how to use the tick accumulator. So, create instruction. Parameter is a seconds from given a tick and the token amount calculates the amount of token received in exchange. Tick value used to calculate the code. Base amount of token should be converted. Address of an RC20 token. Contract uses the base amount denomination. Code denomination. Amount of code token received for base amount of base token. Yeah, now I'm not sure if I should, because I already have a bunch of files. Maybe I should create a solidity one here and put these formulas in. I think it might be a good idea actually. But the thing is, I don't want to put all of them because then I might be, yeah, it's probably going to be confusing. I only want to extract the ones that I think might be relevant to what I'm trying to do. Otherwise, it's just too much stuff and lose too much time researching all the time. So it's better to think about what I want first and then get the formulas based on that, instead of getting all the formulas. So this seems interesting. Get blocking starting tick and liquidity. Given a pool, it returns the tick value as of the start of the current block. Address. So this one I think I'm gonna copy. But it's a very big function. I think it returns 0. I think I'm gonna have to create something, not file, a folder, solidity. And then I'm just gonna do the same thing that I did for Python. The Python and JavaScript is pretty much the same functions that I'm gonna put. I'm just gonna put them in Python, both in Python and in, oh, this is not Python. And in JavaScript in case I wanna use JavaScript libraries instead. For Python, you can, it's gonna give me an error. I don't know why though. Oh, I think it's the indentation, maybe. In Python, there's a library called Brownie that is similar to Hardhat for deploying smart contracts, but I couldn't install it because it looks like you need to do some things because of the environment. So I decided it wasn't worth to spend the time trying to figure out. That's why I'm deciding to go with Hardhat for deploying and then Python for the rest. Free functions cannot have visibility and declared identifier. Oh, I have to import this and put the program solidity at the top. There we go. Because this is obviously using the Uniswap libraries. So let me see. I think I'll go one by one just to see which ones look interesting. Calculates time weighted means of taking liquidity for a given UniswapV3 pool. So where is that? Oh, I think, yeah, it's this function here. Pool. So I'm gonna put this one here until I get to that. Pool address of the pool that we want to observe seconds ago. Also seems interesting. Arithmetic mean take, the arithmetic mean take from harmonic mean liquidity, the harmonic mean liquidity from. I don't know what that is, but I think I'm gonna put this one here. Seems like something that is gonna be useful. Given a tick and a token amount calculates the amount of token received in exchange. So given a tick and a token amount calculates the amount of token received in exchange. And the thing is, how is that tick? How do you decide what is the tick that you're gonna put there? Base amount of token should be converted. Address of. Yeah, this also sounds interesting. So I think I'm gonna probably end up copying all of the functions anyway, because they all seem to be very useful and relevant to what I'm trying to do. Given a pool, it returns the number of seconds ago of the oldest stored observation. Pool address of Uniswap. And obviously, I don't need to put them here because you can just call them directly. But like I said before, I'm putting the stuff here that I think I'm gonna use in the future, so I don't have to search for the library. I can just look in the file, and then I can see which function I want to call. But I won't be calling them from here, obviously. I will be calling them from the abstraction of the contract created by Web3 Pi. Given a pool, it returns the tick value as of the start of the current block. Address of Uniswap pool. The tick that the pool was in at the start of the current block. So this one returns the tick. I guess the tick is kind of like the time, but it's different because it works in blocks, and yeah. Kind of like the trading time where you have the ticks. It's probably the same thing. So obviously you're gonna copy this one. Oh, I already did. So this is this one here. So let me read this. Acquire observation. If the latest observation occurred in the past, then no tick changing trades have happened in this block. Therefore, the tick in slot 0 is the same as at the beginning of the current block. We don't need to check if this observation is initialized, it is guaranteed to be. And so the question I have now is, can I call these functions directly, or do I need to, I think I need to create so I think it's good to put this here as well, because I probably have to access the library first. I think I'm gonna end up copying everything actually, to be honest. They all seem very useful. Given an array of ticks, I'm gonna copy everything, and then because I also don't really know exactly which ones I have to read more the information and understand more how it works and start working on the functions. So then I can filter these things out, but I also don't want to leave this tab open for later, so it's easier just to copy here and continue to do this. And since this one I already put here, yeah, because this was one wasn't a part of the library, it was just here. I'm gonna leave it there. I think I stopped here. Yeah, Oracle library. So I'll be right back. think I'll put some music here. I'll read this stuff. Probably turn on the lights soon as well. So the biggest thing that I need to clarify is which is kind of bothering me, is the uncertainty, not the uncertainty, but my lack of understanding of the formula for arbitrage, which seems very simple, but it also feels like I'm missing things here. Because it seems that it is simple to calculate for specific cases, but in order to generalize for all the cases, then it becomes hard. Yeah, that's the thing. I think the question is the amount and the limits to decide the profit. I think that's the part that is complicated because it's gonna vary from case to case. So understanding that is the priority, I think, for me now. And also, the other thing is also understanding the relationship between the legs of the arbitrage. That's also something that is not really clear to me right now. Because essentially, if you can have a triangular arbitrage, it means you can probably have an infinite amount of pairs. So this is the thing that is not really clear to me, is what exactly are you spotting when you see the differences? So for example, why would you do 2 legs instead of 3 legs? And I think I know the answer to that, but it's still not very clear to me how this scales through as you put more legs into it. Because ideally I would like to do something where I can dynamically figure out the amount of legs I can put, but it seems very complicated. So liquidity accumulator. The liquidity accumulator stores the value of seconds in range liquidity at the time of the observation. Liquidity accumulator value increases monotonically and goes by the value of seconds in range liquidity per second. To derive the harmonic mean liquidity over an interval, the caller needs to retrieve 2 observations, one after the other. Take the delta of the 2 values, then divide the time elapsed. I think I already read this. The in-range liquidity accumulator should be used with care, because the current tick and the current in-range liquidity can be entirely uncorrelated. There are scenarios in which taking the arithmetic mean tick and the harmonic mean liquidity over the same interval in a pool can inaccurately characterize this pool relative to another. For example, if the current tick on pool A is 0 for 5 seconds and is 100 for 5 seconds, the tick accumulator will be 50. If over the same interval the in-range liquidity was 5050, the harmonic mean liquidity will be 99. I don't understand what this harmonic mean liquidity is actually. In-range liquidity. So the mean liquidity is the price. It's between the ticks. If you over the same interval, the in-range liquidity was 5050. Liquidity will be 99. Compare this to pool B, composed of the same assets, where the tick was 50 and the in-range liquidity was 99 for 10 seconds. The accumulator values will be identical, but the underlying behavior is of course quite different. I think I understand what they're saying on a concept level, but I don't understand these details here. But they're pretty much saying that you can have inaccurate observations by just aggregating the averages of things, pretty much. So it looks like it is something, some way, but for example, if you have a high standard deviation and you get the mean, you're probably gonna get something, but then you're not taking into account the outliers. That's pretty much what they're talking about there, I think. But the specifics I don't really understand. Deriving price from a tick. When we use active tick or otherwise to refer to the current tick of a pool, we mean the lower tick boundary that is closest to the current price. When a pool is created, each token is assigned to either token 0 or token 1 based on the contract address of the tokens in the pair. Whether or not a token is token 1 or token 0 or token 1 is meaningless. So that's another point of confusion that I just remembered is if I start with one token and end up with another one, it's not going to be the same if I did the other route. So the challenge is how to transform that into code to check for all the possible variations of different routes. I think that's another thing that I have to think about. So maybe I should write that so I can think. So I probably will write this down the triangular arp file. Maybe I'll rename this to just arbs, because I can put more than one then. How to build an algorithm that checks for all the routes, all possible routes given an amount of flags in an arbitrage. So the goal is taking the tokens that are part of the arbitrage and then I have to also think about how does this relate to the formulas, because if the tokens are on different exchanges, obviously the formula for the slippage, not only the slippage but the fee and the difference in prices is going to be different, so the amount is going to be different through the routes. So how to correlate different formulas, different formulas with the arb routes. When a pool is created, each token is assigned. It's only used to maintain a fixed assignment for the purpose of relative valuation and general logic in the pool contract. Deriving an asset price from the current tick is achievable due to the fixed expression across the pool contract of token 0 in terms of token 1. An example of finding the price of WIF in a WIF USDC pool, where WIF is token 0 and USDC is token 1. You have an oracle reading that shows a return of tick cumulative as 70,000, 1,070,000, with an elapsed time between the observations of 10 seconds. You can derive the average tick over this interval by taking the difference in the accumulator values. So the end minus the beginning and divide by the time, which is the average, which goes into the standard deviation thing I was talking about. With a tick reading of 100,000, we can find the value of token 1 USDC in terms of token 0 wrapped with by using the current tick as I in the formula. So this 6.1 in the white paper. Tick reading 100,000, we can find the value of token 1 in terms of token 0. by using the current tick as I. So it's pretty much, it's elevated to the medium. So I think I'm gonna write this down here because it's relevant to the Uniswap thing. So is to find the value of token 1 in terms of token 0. So value by tick. So here's token 0, token 1, tick. Actually, it's better if I do it like this. So token 1, tick. First token. I don't think we need to put this actually. Just the tick. You find the value of token 1 in terms of token 0 by using the current tick. Which is the average based on time interval. So final minus initial divided by time. But the only thing I don't understand is what is these values here? Tick cumulative. So I guess it's both for both pairs. Example of finding the price of wrapped ETH in a wrapped ETH USDC pool. Where final is an initial. Our values for the cumulative tick. So token 1 is USDC, token 0 is WIF. So 0 is the token, so maybe I should put token 0, token you are trying to get the price. Token you are comparing 0 to. So T cumulative is probably the price of both of them, of the pair. We can derive the average take over this interval by taking the difference in accumulators and dividing by the time elapsed. I don't think they gave this formula. Maybe in the Oracle library you can find this formula. I think it's the one. Let's see, cumulative tick. Got block starting tick and liquidity. But I don't know for sure if it's this one. Maybe it is actually. Because you're passing the pool. And then it's gonna return the tick and the liquidity. So I think I'm gonna use this one to get the cumulative. Given a tick and token amount, calculate the amount of token received in exchange. Maybe this one already returns the final thing. Yeah, but then you need to pass the array of ticks. It doesn't seem like this has a return function as well. A return statement. Okay, so I get the... Oh, I should write the function. Forgot. I think it was this one. Take liquidity, it was this one. Use function phone. Oracle library. Gas, tick, cumulative. First arguments. Get return. So the formula is gonna be price is equal to we can find the value of token 1 is in terms of token C by using the current tick as I in the formula. So it's pretty much P equals 1.00, but it's almost irrelevant actually. Times tick. And then I make this I don't understand actually. This doesn't make sense here. He's not using P here, he's using something else. Using this number, so. And maybe I have to look at the white paper now with this formula. 6.1. So here. So actually there is a tick at every price P that is an integer power of 1 x by. Thanks for the follow. See if I can see her name. M. Toley. This has the desirable property of each tick being 0.01%, 1 basis point price movement away from each of its neighboring ticks. For technical reasons explained in 6.2, higher pools actually track ticks at every square root price that is an integer power of the above equation transformed into a square root price space. Price tick 0 is 1. And liquidity is added to a range if one or both of the ticks is not already used as a bound in the existing position that ticks is initialized. Not every tick can be initialized. The pool is instantiated with a parameter tick spacing. Another thing that I just thought about is I actually can look at the code, source code actually. It might be a lot better instead of having to write these functions again. The only resistance I have to that is because it might take me a long time to find the specific functions that I want. Yeah, but I think it's probably smarter to just spend the time looking at the source code and seeing their implementation, because then I can also use that in order to figure out how to do the functions that I want to do for this thing that is outside of the library. If fees have been earned in some ways, liquidity can be thought of virtual liquidity tokens. Changes for a given change in price. You want to change this music, but didn't like that much. But what is P here? That's the thing. I guess it's just a function, but it's converting the I into this exponential thing here, which is gonna be slightly different than the initial value. But then how does that translate to here? Because this is probably USDT, and then it's gonna be equal to this, so I assume it's just P times. But then why would you use P here if you're just using the constant? That's the part. Oh, so the I is the 100,000. That's why I'm confusing. So it's not the tick. With a tick reading of 100,000. Oh, okay, so the tick is the price. Yeah, that's what I'm getting twisted here. So let me read this again. I think I'm confusing the tick with the time instead of the price, which is it's probably both. Is active tick or otherwise referred to the current tick of a pool, we mean the lower tick boundary that is close to the current price. Each token is assigned to either token 0 or token 1 based on the contract that acts as the token. An example of finding the price of with where token tick cumulative as 70,000 with an elapsed time between the observations of 10 seconds. So that's the part that is confusing. Because I don't understand what they mean by this. That's probably why I'm getting confused here. tick accumulator. The tick accumulator stores the cumulative sum of the active tick at the time of the observation. The tick accumulator value increases monotonically and grows by the value of the current tick per second. Or is monotonically. To derive the arithmetic mean tick over an interval, the caller needs to retrieve true observations, one after the other. They take the dot of the true values and divide by the time lapse between them. Map from the tick accumulator is also covered in the white paper. Arithmetic mean tick to derive a price correspond to a geometric mean price. For an example of how to use the tick accumulator. So I guess it's this function here, but it's just very confusing the way that they explain this. The elapsed time between the observations of 10 seconds. We can derive the average tick over this interval by taking the difference in accumulator values. Divided by the time elapsed. By tick reading of 100,000, we can find the value of token 1 in terms of token 0. By using the current tick as I. Oh, 100,000 is not the price, is this calculation here. Oh, so I see what they did. They pretty much did replace P here. So I think I was right in the beginning. So I can do it like this. And then it's gonna be the tick here. But then I probably don't need this to shoot tokens, that's the thing. Because these I'm gonna be getting already from the... So, yeah, that's the thing that... I guess that's why it's confusing, because it's also based the values of USDC based on the value of WAF based on USDC. So the tick also has to do with the value of USDC. So I think that, yeah. Yeah, because that's the thing, I can't specify. The formula only uses the tick, but it doesn't says anything about because it's already, the tick cumulative is already something that is related to both both coins beforehand. So I'm just trying to think about how can I specify, or if I do need to specify. Because I'm probably gonna forget when I'm gonna use this which token is the one that I'm getting the value from. So I guess the question I have is with the cumulative, how do I know which token is this referring to? So in this case it's USDC. So I guess it's always going to be token 1. And this would be... Yeah, this would be the answer already. Turn P. So ticket the price of token 1 in relationship to token 0. That's what it is. The cumulative. Now the price is when you elevate to this number, which is slightly different. But the price, yeah, the cumulative would be the price of the relationship between them. It's very confusing. So I guess I don't need this true here. And I can erase this. So I get the price from the function, and then yes, so I need to see what are the arguments that this function is receiving, so I understand better how it works. Just get blocks starting, tick, and liquidity. So it's receiving the pool. Returns the tick value of the start of the current block. Yeah, but how do I know what is the coin, the first coin, and the second one that is comparing to? Because a pool could be both ETH USDC and USDC ETH. I'm not sure if there's two different pools for that. It seems like it doesn't make sense. It seems like it would be only one pool. The tick that the pool was in at the start of the current block. Yeah, so I guess if you wanted to know the price of wrapped ETH in relationship to USDC, you would do the opposite. So take the square root. Yeah, I'm not sure. Or the log actually. Put the log in both sides. Past the 100,000. Still a little bit confusing, but I think I'm gonna continue. Maybe when I read the white paper is gonna be a little bit more clear. And I also need to see if I can figure out a way to understand this bowl thing. That's probably the main point of confusion. Ticks are signed integers and can be expressed as a negative number, so for any circumstances where token 0 is of a lower value than token 1, a negative tick value will be returned by tick cumulative. And a relative value of 0 will be returned by a calculation of token 0 in terms of token 1. On layer 2 rollups, optimism where every transaction is confirmed as an individual block. The block.timestamp of this blocks, however, reflected the block.timestamp of the last L1 block ingested by the sequencer. For this reason, Uniswap pools on optimism are not suitable for providing Oracle prices, as the high latency block timestamp update process makes the Oracle much less costly to manipulate. In the future, it's possible that the optimism block.timestamp will have much higher granularity, with a small trust assumption in the sequencer, or that forced inclusion transactions will improve Oracle security. More information, blah blah blah, range orders. Customizable liquidity positions along with single-sided asset provisioning allow for a new style of swapping with automated market makers, the range order. In typical order books, book markets, anyone can easily set a limit order to buy or sell an asset at a specific predetermined price, allowing the order to be filled at an indeterminate time in the future. With UniswapV3, one can approximate a limit order by providing a single asset as liquidity within a specific range. Damn, that sounds both complex and interesting at the same time. Like traditional limit orders, range orders may be set with the expectation they will execute at some point in the future. The target asset available for withdrawal after the spot price has crossed the full range of the order. Unlike some markets where limit orders may occur, fees, the range order maker generates fees while the order is filled. This is due to the range order technically being a form of liquidity provisioning rather than a typical swap. Possibilities of range orders. The nature of AMM design makes some styles of limit orders possible, while others cannot be replicated. The following are 4 examples of range orders and their traditional counterparts. The first two are possible, the second two are not. One important distinction: range orders, unlike traditional limit orders, will be unfilled if the spot price crosses the given range and then reverses to recross in the opposite direction before the target asset is withdrawn. Oh, so I see. Probably because the same way that the atomic transactions work. I guess, not sure. While you will be earning LP fees during this time, if the goal is to exit fully in the desired destination asset, you need to keep an eye on the order and either manually remove your liquidity when the order has been filled, or use a third-party position manager service to withdraw on your behalf. Take profit orders. The current price of DAI ETH pool is 1500 DAI ETH. You would like to sell your ETH for DAI when the price of ETH reaches 1600. This is possible as the price space above the spot is denominated in the higher valued asset. If you can provide the ETH at a price of 1600 DAI, have shorted the order filled when the spot price crosses your position. So I don't think I'm gonna use this, but it definitely changes the game, because then people are gonna start seeing these orders and making decisions based on that. So it's a closer approximation of a normal centralized exchange. And there's also possibility for then making predictions and then putting things in place based on that, just like in a normal trading, I guess. Buy limit orders. The current price of DAI ETH pool, you expect that it will rebound after it drops to 1000 market downturn, so you like to place range orders. As the above examples show, in UniswapV3, the two paired assets in the given pool are separated above and below the spot price. There are price asset available above the spot price and the lowered price asset below. Following examples show limit order styles that are unable to be replicated due to the separation of assets in price space. And stop orders. The current price of DAI ETH pool is 1500. So the price shot up to 3000 once it hits 2000, so you'd like to place a range order from DAI to ETH at a price of 2000. It is not possible as the price space above 1500 ETH is denominated in ETH, and thus you cannot provide the DAI necessary at your desired price to be swapped into ETH. So the price is always denominated by the coin that is worth. has a higher value. The price space above 1500 DAI is denominated in ETH. Stop loss orders. The current price of a DAI pool is 1500. You expect that once the price of ETH drops to below 1000, it will tank to 200. So you'd like to place a range order from ETH to DAI at the price of 1000. This is not possible as the price space below the spot price is denominated in DAI. And so you cannot allocate the ETH necessary at 1000 to be swapped into DAI. I don't fully understand this, but I think it makes sense because it's probably because the way that the rate works, because it's based on the liquidity pool. So there are probably some exploits there if they allowed this to happen. But I don't really understand exactly how it works. Because every time you trade from one asset to the other, it's gonna change the liquidity, which is gonna change the price. So that's probably why this works like this, but yeah, don't fully understand. The fees due to your liquidity position will be denominated in both tokens of the given pair. In any of the above examples, after swapping ETH for DAI or DAI for ETH, small amount of both ETH and DAI will be due to your account as liquidity provisioning rewards. Approaches to concentration when setting range orders are up to the user. Selecting a wider range may generate more fees if there is price churn within your range, at the cost of increasing the risk of having your order unfilled if the spot price reverses before completing the full range. Let me see if they're gonna talk about the rate. Yeah, I don't see anything about rate here. Trying to think what's gonna be the best time to switch to the white paper instead of continue to read this. Because this is not the only exchange that I'm gonna look at. I'm gonna look at all of them. I think the most important part for me now is getting the rate. And then I probably, after this, I'm probably not even gonna look at the other ones. I think I have to sit and think about the formula that I was talking about earlier to figure out the routes and how to translate the arbitrage into coding format. If all this, and how to find the relationship between the rates and the arbitrage. Swaps are the most common way of interacting with the Uniswap protocol. For end users, swapping is straightforward. A user selects an ERC20 token that they own and a token they would like to trade for it. Executing a swap sells the currently owned tokens for the proportional amount of the tokens desired, minus the swap fee, which is awarded to liquidity provider swapping with the protocol commercially processed. Using web interfaces websites to swap with the Uniswap protocol can introduce additional permissions structures, resulting in a different execution behavior compared to using the Uniswap protocol directly. Swaps using the Uniswap protocol are different from traditional order book trades in that they are not executed against discrete orders on a first-in, first-out basis. Rather, swaps execute against a passive pool of liquidity, with liquidity providers earning fees proportional to their capital committed. Yeah, so this could be explained more. So I think what they mean by this is that in traditional exchanges you have the first person that places the order gets the order fulfilled, and in the swap it's against the pool, but it's not very clear. In a traditional order book market, a sizable market buy order may deplete the available liquidity of a prior limit sell and continue to execute against a subsequent limit sell order at a higher price. The result is the final execution price of the order is somewhere in between the two limit sell prices against which the order was filled. Price impact affects the execution price of a swap similarly, but is a result of a different dynamic. When using an automated market maker, the relative value of one asset in terms of the other continuously shifts during the execution of the swap, leaving the final execution price somewhere between where the relative price started and ended. Okay, so I think I get now what they're saying. It's pretty much in traditional market, the order is gonna fulfill the other side, but in automated market makers, the order fulfills based on the formula of the ratio of the liquidity pool instead. So I have to think a little bit about this. It changes the dynamic because, yeah, it's programmatically in automated market makers, and I'm gonna change this song here. It's programmatically in automated market makers and is supply and demand. Yeah, but then because if you have multiple people, that's the thing that is different. Because you also have the supply and demand, but is on top of that you have the rate. So if you are executing an order for ETH and you have USDC and you're buying a bunch, it's gonna change the price based on the ratio. But then if other person is executing the other way around, then there's gonna be less difference. It's gonna balance it out. So the less people that have, the bigger the spread is, the more you pay. But it's different than the traditional ones, because in the traditional ones, if there is a spread, then there's no liquidity. The orders don't get fulfilled until someone closes the gap. So I think that's the main difference here. So in this, the spread doesn't exist. It does if people are not willing to pay the higher price, for changing the ratio of the amount that exists in the pool. So it means on pools that have higher liquidity is better for doing arbitrages, because obviously if there is less, you're gonna change the price a lot more. But then it's a trade-off, because you also need differences in prices. So there's a balance there, I think. Yeah, I have to calculate how much. This is the tricky part, I think. It's the difficult part. Because you have to calculate how much you can move the price based on this liquidity and the other prices of the other exchanges in order to get the profit, the maximum amount, which is very hard to think about, because what is needed is the volume, and I guess I can get that through this formula here, get the liquidity through this function. Yeah, that's one thing. That's the question. How do you calculate the difference? I guess that's where the rate comes in. If you have the amount of liquidity, you can use the rate to calculate the loss, the relationship between the quantity and the loss. Yeah, so I guess it goes into the formula. It's like a link between swaps. If you wanna estimate. This dynamic affects every swap using the Uniswap protocol, as it is in an inextractable part of the AMA design. As the amount of liquidity available at different price points can vary, the price impact of a given swap size will change relative to the amount of liquidity available at any given point in price space. The greater the liquidity available at a given price space, the lower the price impact for a given swap size. The lesser the liquidity available, the higher the price impact. Approximate price impact is anticipated in real time via the Uniswap interface, and warnings appear if unusually high price impact will occur during a swap. Anyone executing a swap will have the ability to assess the circumstances of price impact when needed. There's also the other question of how can someone manipulate this by placing very big orders, but then yeah, you would need to have enough incentive in other exchanges to do that. It's kind of like you're faking the price temporarily by placing these large orders, but I'm not sure if there is a use for that or if it makes any sense. The other relevant detail to consider when approaching swaps with the Uniswap protocol is slippage. Slippage is the term we use to describe alterations to a given price that could occur while a submitted transaction is pending. When transactions are submitted to Ethereum, their order of execution is established by the amount of gas offered as a fee for executing each transaction. The higher the fee offered, the faster the transaction is executed. The transactions with a lower gas fee will remain pending for an intermediate amount of time. During this time, the price environment in which the transactions will eventually be executed will change, as other swaps will be taking place. Slippage tolerances establish a margin of change acceptable to the user beyond price impact. As long as the execution price is within the slippage range, 1% of the transaction will be executed. If the execution price ends up outside of the accepted slippage range, the transaction will fail, and the swap will not occur. That's another problem, because obviously if you have a transaction which is an opportunity, someone can go in front of you, front run you, and then make your transaction cancel because of your slippage. So I have to think about how to prevent that. Maybe set the higher slippage, but then you're also losing value, because you also have to pay gas. A comparable situation in a traditional market would be a market buy order executed after a delay. one can know the expected price of market buy order when submitted, but much can change in the time between submission and execution. Safety checks, price impact, and slippage can both change while a transaction is pending, which is why we have built numerous safety checks to the Uniswap protocol to protect end users from drastic changes in the execution environment of their swap. Some of the most commonly encountered safety checks: expired, to ensure there occurs if a swap is pending longer than a predetermined deadline, sufficient output amount. When the user submits a swap, the Uniswap interface will send an estimate of how much of the purchase token retrieve. But nothing about the formula still. Some formulas here. But this is only for liquidity provider side. I think I'll go faster to this and just stop if I see the formula. If not, I'm gonna read the white paper because it's more likely that it is in the white paper than it is in here, this thing. Oh, this is very good. Still very hard to understand. Or maybe I should just take the formulas and write it down. Because I don't understand these virtual reserves here. I think they talked about this a little bit, but I didn't understand. I think I'm gonna close this, keep going through the site, and then read the white paper. I'm actually gonna read less as well because I'm getting tired. So I'm gonna just get the music. I like reading because it helps me focus and retain more information, but I'll copy this one probably here. I just realized now that I probably should make another file for this. But then the issue is if I'm gonna do multiple exchanges. I think I'm just gonna leave on this file. And I'm gonna copy these functions from here actually and put it on the other file. I don't know how to make, so it's like this. Other functions. So these are just the interface, not the function itself. Let's see if they have the function there. I guess this is the end of the thing. Yeah, this is what I was thinking. So you should pass this as inputs. I'm gonna copy all of this, probably necessary. I think here is missing the closing bracket. I'm just thinking about, I'm probably gonna do this now, actually, sure. Replace this with a function. Maybe it's better to put like this. Then I think I have to make it public. And that's the thing. I think I have to declare them here. And then I wouldn't use this, I would use memory. I think it goes here. Because the issue is that here it takes more. It costs gas, and if you put it in function, it doesn't. But then the question is, what do I put here? Because if I just return the tree, then I don't know if it makes sense. I guess it does because it changes the place that they are gonna be stored. But then I have to think about the other things, how they are using these contracts. Yeah, here wouldn't be die. So maybe I just return the tree and then I use the implicit thing, the structuring thing. But I'm not sure if I can call a function here. Because I also have to pass. Oh, I can declare here and make it first address, second address, third. Yeah, but then the problem is I probably have to pass these variables. Yeah, I don't understand. I have to think more about this. I'm probably gonna continue and then think about this later. And I guess the reason why this is difficult is because I don't know yet how I'm gonna be populating these addresses of these contracts. That's the thing that I'm unsure about. So I guess it's the contracts of the swap, but yeah. How would I... How would I be calling this, and then how would it interact with the other ones? So I'm trying to think about a way as well to not have the variables outside of the function, only using memory. Because if I call this function inside of this one, then I need to change the parameters it's gonna receive. Not sure if that's good. Thank you for the follow. Wyatt_Earth. Not sure if I said that correctly, but I guess it's better to look at this later, actually. Because I need to follow as well the kind of the blueprint that I have, the vision, so I don't get lost and sidetracked. The biggest priority right now is getting the rate for the market. Then I have to think about, because that's is the stuff that is bothering me. The exact formulas based on the rate, and think about how they connect with each other. Because then once, yeah, it's better to break down the problem into smaller parts. That's the thing. So I need to follow this step by step that I have in my mind. It's hard because a lot of information, a lot of things to think about. Not only on Uniswap, but all the other stuff. So I think if I get the rate first, and then getting the rate, and then figuring out how to calculate the optimal arbitrage, I think that's the main two things that I have to focus. Once I have that, then I can start thinking about these functions. Yeah, that's probably better. So I think it's better to... I'm probably gonna come back to this documentation as well. I think it's better to move on to this documentation here. This white paper. Automated market makers are agents that pool liquidity and make it available to traders according to an algorithm. Constant functions market makers, a broad class of AMLs of which Uniswap is a member, have seen widespread use in the context of decentralized finance, where they are typically implemented. I think I'm gonna skip this actually, the introduction. It's probably stuff that's already read. Concentrated liquidity. The defining idea of UniswapV3 is that of concentrated liquidity bounded within some price range. In earlier versions, with liquidity was distributed uniformly along this equation. Reserve score, where x and y are respective reserves of two assets x and y, and k is a constant. So I guess the reserve determines the price. It's the same thing. Maybe. Yeah, maybe. No, I'm pretty sure that x and y are the prices of the assets. To provide liquidity across the entire price range 0 to infinity. This is simple to implement, allows liquidity to be efficiently aggregated, but means that much of the assets held in a pool are never touched. Having considered this, it seems reasonable to allow LPs to concentrate their liquidity to smaller price ranges than 0 to infinity. We call liquidity concentrated to a finite range of position. Position only needs to maintain enough reserves to support trading within its range, and therefore can act like a constant product pool with larger reserves. We call this the virtual reserves. So this part is important. Call liquidity concentrated to a finite range of position. Position only needs to maintain enough reserves to support trading within its range. So I get it now. So whatever the range is the virtual thing, I think. So it's kind of like a subsection of the total amount that fluctuates over time. It's like the pool, the virtual reserve is like the iceberg, the tip of the iceberg, and the total amount of liquid thing is underneath the ocean. And then as the waves fluctuate, the amount goes up and down. I guess that's how it works. Specifically, a position only needs to hold enough of assets X to cover price movement to its upper bound. Because upwards price movement corresponds to depletion of the X reserves. Similarly, it only needs to hold enough of Y to cover price movement to its lower bound. Depicts the relationship for a position on a range and a current price. And Y real denote the position's real reserves. When the price exits a position's range, the position's liquidity is no longer active, no longer earns fees. At that point, its liquidity is composed entirely of a single asset, because the reserves of the other asset must have been entirely depleted. If the price ever re-enters the range, the liquidity becomes active again. The amount of liquidity provided can be measured by the value L, which is equal to square root of K. The amount of liquidity provided can be measured by the value L, which is equal to K. But what is K and what is... So L is the liquidity provider, but what is K? K is the constant, I think. The real reserves of a position are described by the curve. So these formulas are important too. So these ones I'm gonna write it down here. Oops. So K is the constant. The only question I have is whether or not I put the tokens. I think I'm gonna put it. liquidity provided pass k L equals, I think I can do a square root of k like this. Probably need a library for that. I think I'm gonna do this one separately, so liquidity provided. And here I have to put k is the rate between tokens. I can also do it like this. I think that's the easiest way, so that's what I'm gonna do. Yeah, math, that's square root. So the real reserves of position are described by the curve. So the real reserves. So it's gonna take X, L, PA, L. This curve is a translation of formula 2.1 such that the position is solvent exactly within its range. So it's pretty much the same slope, I guess, just shifted both in X and Y by this factor. But what is PA and PB? Point A and point B. And then what is X? But it can't be point A or point B because that would be true coordinates and not a value. Or maybe it's the value of Y at that point. It's kind of confusing. Oh, here. I didn't read this. Maybe I read and didn't pay attention. This should hold enough of asset X to cover price movement to its upper bound. As upwards price movement corresponds to depletion of the X reserves. Similarly, it only needs to hold enough of asset Y to cover price movement to its lower bound. Range for a position on a range PA, PB. So PA, PB is the range. And the current price PC, which is within the range. X and Y denote the position's real reserves. When the price exits a position range, the position liquidity is no longer active. The question is how I'm gonna put this into code format. That's the problem. Put this function because it's arbitrary. So how do I determine the range here? There's just 2 points on the function, so yeah, X and Y. So it's gonna be K divided by X divided. I would actually need to have maybe an integer. No, integer is gonna be the area. To find the distance, I'm gonna have to subtract. Because x is gonna be a minus b, y is gonna be a minus b. And then I put on the equation, I think. I can do this with paper, but I'm thinking about if I'm thinking about this the correct way. Because I only want the range and I don't want the equation. I'm probably gonna have to provide the values of b and a in the arguments, I think, to do this. For both x and y positions. I think the amount of liquidity provided can be given by this formula because it's the integer of the curve there, given these limits, but I'm not really sure. Probably not, because the integer would be the area and not the... Oh, but actually it is the area. Yeah, no, I'm forgetting. Oh, it's a bunch of stuff. I obviously understand it, but it's hard to think about how to put this into the code there. I guess what's not so clear to me is that, yeah, the amount has to be the area, I think. Because the area contains the points, the sum of the points, which are the values that represent the amount at each point in the curve, which follows this x, y, k thing. Yeah, so the equation is y equals k divided by x. That's the equation. But then how can they... yeah. Because it would be y equals x times square root of k. No. Y equals x times k elevated by minus 1. Then I take the integer, becomes 1. And then x becomes the square root, I think. No, that doesn't make sense. because it would be a constant, which is 0, and then x would be 1, the integer of x. Oh, actually it's more complicated than that, because yeah, I have to see actually. I'm probably gonna have to research this, because I don't remember really well. And it's not the integer from 0 to infinity as well as the integer from b to a. So you probably have to replace the values when you calculate to find the total amount. I'm trying to think about if I can do this without having to research the integer, or if I'm not understanding really well how it works. So maybe PB and PA is the K, actually. The K for that point. I think that's what's happening here. But then that would be equal to L, doesn't make sense. Oh, actually kind of does, because no, it doesn't. I might have to write this down and solve it, but don't wanna do it. Because I would have to solve the equation to see if what I think is going on is going on. But I wanna think if there's a way. I wanna see if I can figure out what this is without having to write anything down. Oh, so why real is the difference between the point? Oh, yeah, because it's a little bit confusing here. So now I get it. So x real is the distance, is c minus b, essentially. Cx minus bx. And y real is... this is pretty much the distance between these points. Denote the position's real reserves. Also, the real reserves are A and B in relationship to C, which is the virtual one. This thing is seriously confusing me. So I guess this line here is C. But then why the shift here? I don't understand this. I guess it's shifting by this, but... I remember there is some easy way to do that. Basically, whenever you either subtract something to a function, you're just moving the function either horizontally or vertically, but I don't really remember really well how it works. this part here is the one that is confusing to me. Do I have a single asset because the reserves of the other assets must have been entirely depleted? Enters the range. The amount of liquidity provided can be measured by the value of L, which is equal to K, which is square root of K. The amount of liquidity provided can be measured by the value L, which is equal to the square root of K. Yeah, but why though? That's the thing. Because it doesn't make sense even if you take the integer. I don't think that works. Yeah, but then you would have the limits as well, which I'm not taking into account. So it would be the log n of x. And that's probably why then. Because y equals log n of x, and then... No, but it still doesn't make sense to me. So it would actually be log b, log n of b minus log n of a, I guess. And maybe if you solve that, you get square root of the... Yeah, it doesn't make sense. And I'm probably thinking about this the wrong way, I think. The real reserves of position are described the curve. So I have x and y, which I assume are the real x and y. L, which is the liquidity. And this P, which are the points, the range. I guess, yeah, what I could do for now is just put the points and then keep reading and see if it clarifies in my mind later. But then the biggest problem is how exactly I'm gonna go about structuring this, because I don't know how I'm gonna use it. But I guess I'll just do it as simple as I can. And maybe PB, BA. I should probably put like this so I don't get confused. Oops. Yeah, now I don't know. I'm gonna put here that it is the real X point of the real reserves. But I don't really know for sure. The real reserves are position and describe the curve. Okay, so initial point of the range, final point of the range. I don't think it matters if I put parentheses there, so I'm not gonna put it. And then here, outside of this, times here I do have I'm gonna put just in case. Oh, I can do that as well. So I can do this whole thing multiplied by 0.5. I think I understand it on the conceptual level, but when it comes to this equation, I'm not really sure if I fully get it. You're free to create as many as they see fit, each on its own price range. In this way, LPs can approximate any desired distribution of liquidity on the price space. Moreover, this serves as a mechanism to let the market decide where liquidity should be allocated. Rational LPs can reduce their capital costs by concentrating their liquidity in a narrow band around the current price and adding or removing tokens as the price moves to keep their liquidity active. And the other thing that makes this a lot more complex is that you're gonna have a lot of different people choosing different liquidity ranges, and I guess the aggregate of all those differences is gonna make up the virtual reserves. And then obviously the real reserves don't fluctuate because it's the total amount. They fluctuate actually based on withdrawing and depositing, but I still don't think. Maybe I should spend more time here trying to think about what this PA and PB means here in the equation. Because they follow the y equals x divided by k, y equals k divided by x. But I'm not sure if they're supposed to be the value of y. I think it's probably that, because yeah, now I think I understand. So x is the real plus the difference here, That's what's happening. So it's plus this difference to find the point here. And then y plus the difference. I think I get it now. So PB is actually XB, I think. Oh, is the value of y on that point, I think. I'll be right back. I'm trying to think about how do you get square root of k and how do you get L to the power of 2 from the equation of x times y equals k. It doesn't seem to make sense to me. Only if the values of x, y are the same. But yeah. Because then k would be x times y. Should be the same. Should be L to the power of 2. So maybe that's what they are doing here, but it doesn't make a lot of sense to me. Because then that wouldn't be the total amount of liquidity provided. That's what I don't get. Because in my mind, the total amount is... Oh, actually, maybe I'm thinking about it the wrong way because it's 2 different coins. Yeah, but the total amount has to be, of the overall pool, has to be the area of the curve. Or the integer of the equation, I think. Which is the integer of I equals k divided by x. But maybe that would give me the total amount of Y reserves. That's the thing. Thanks for the follow. Uh, Typing Kate. So I do think what makes the most sense to me is this thing here. Just because of the way that he explained. So they're probably trying to represent the x plus this distance here, which is this. That's what I think. So this would be the C point. And then same thing for A. Which would be... Yes, I'm trying to figure out what does this PB and PA means here in this equation. To understand, I'm not sure you're familiar with Uniswap V3. Because there's this concept of real liquidity and virtual liquidity. And virtual liquidity is the range of the real liquidity that people are trading. People are setting up to provide liquidity. Oh, really? Yeah, I'm not sure. I'm not familiar with V2, so I'm not sure what changes from V2 to V3. I'm somewhat very little familiar with V1. But as far as I understand, you have the real liquidity, which is the total amount of liquidity in the pool. And then you have the virtual liquidity, which is the range that people set to provide liquidity. Because, for example, in the stable coin, it only fluctuates between 0.99 and 1.1. So whenever the price is not in the range, the other amount of liquidity is not being used. So it's more efficient to allocate, to decide what's the range that you're gonna allocate liquidity for. And then they came up with this concept of virtual liquidity, which allows you to set the range. So if the price goes outside of the range, you're no longer taking fees, getting the profit from the fees, but you are the same, and at the same time you're not offering liquidity. And then the equation is this one to determine the virtual reserves. But it's really confusing because I don't understand. I think, yeah, they're going from this one to this one here. But it's very... I don't know as well. They say that the total amount of liquidity provided is L, which is equal to square root of K. But I don't know how they achieved that, how they got to this conclusion. And I assume K is the formula X times Y equals K. And then that this portion is probably... I don't know if this makes sense, but it's probably X real. Yeah, X at B, at the B point, plus this thing here, which will give the X real. So I think this portion is X real, I think. But I'm not really sure. And this one is Y real. So, yeah, what do you think about it? And the reason I'm doing this is so I can put it into coding format. I want to translate this into code in case I want to use it later. The confusing part is the way that they draw this here. Because it seems like they're saying that the real reserves are the shift from this curve here. And it shifts by this amount, I think. But then I'm not really sure. Yeah. So maybe this curve here is the connection between these two outside here. And that would be the real. But then here it says that this is the virtual. So that would make sense. So the shift has to be to the left, but the way I understand it, the virtual curve is like an x times y equals k, other virtue style representation of the liquidity, but it's only valid for the current stake. And the way things are implemented, it is exactly equal to the real curve, which is shallower because it only includes the liquidity provided in the current stake, but shifted diagonally so that it fits within the virtual curve, which includes liquidity outside of the current stake. Yeah, but it's very confusing. I guess I'm also having trouble with understanding this. What is necessarily a tick? I don't think I really understand that really well. The way that I'm conceptualizing right now is just like it is in normal exchanges, where a tick has the orders, then has the closing and the opening, but I'm not sure if that's a good representation. Yeah, V2 is easier probably. V2 to be honest. I don't know. It's because even if it's hard to understand, I want to push myself to do it. I think it's better. Because I already read a bunch of things about UniswapV1 and watched a bunch of videos, so I kind of get it. I understand in the conceptual level what's happening, but it's just the mathematics here that is kind of confusing. Mainly these points here. I think I understand the concept of virtual reserves as well, where you pretty much, they allowed people to set a range to provide liquidity instead of having people put, because it's just more efficient to allocate the resources that way, because then you can use the remainder resources that weren't doing anything to do something else. So I think I get that, but... And I remember as well that there are concepts in mathematics that allow you to push the slope, maintain the, let's say, the curve, but push it either in the x or y direction. But I don't remember really well how it works. I think you just increase or decrease the amount. But here it doesn't make sense within this equation here. So specifically the Zell, it would be good if they explained how they come to this conclusion here. Because to me it makes more sense that the total amount of liquidity would be the integer of these 2 points. So the integer starting from A and going to B. And that would be the total amount of reserves because it's the area of the curve. The translation, if you think of the x and y components and then the L square root point B and L square root point A components. Yeah, that's what I was thinking, right? But then y is going to the left. Doesn't that mean that the real reserves are smaller than the virtual ones? Because if you think about the total reserves as the total amount that exists in the liquidity as the area of this curve here, then this is saying that the real reserves are smaller than the virtual ones? Like, how is this possible? Aren't the virtual reserves a subset or a range of the real ones? It doesn't make a lot of sense. I guess it has something to do with the C point, the price of C, but I can't make the connection there. Maybe I have to think a little bit more and I will be able to. Maybe I'm thinking the other way around. Maybe the virtual reserves are the total amount that exists, and the real reserves are the ones. Yeah, but then that doesn't make sense as well. Maybe if I continue reading, it's gonna clarify this. Or I can search for the mathematics and try to see if I understand it better. Oh, so maybe what they mean by total liquidity is the point itself. That's what I think is the confusion. Because the point is in the graph is the total amount of reserves for X and Y at any given time. That's what I think I'm confusing here. Because I'm seeing X and Y as prices, but it's actually reserves. Yeah, so the total amount of liquidity wouldn't be the area of the graph. The total amount of liquidity is just the point. The total amount of reserves, which is the amount of liquidity, I think, is just the point in the graph. So that's why in the point C, so the point C is probably the point where X equals Y. And that's why the total amount of liquidity there is square root of K. I think that's it, yeah. That's probably what's happening here. It's the only thing that makes sense in my mind, at least. And then this is the K, the new K, for the virtual one, which is X plus this distance and Y plus this distance. Yeah, but then that doesn't make sense, because when you change the points, X and Y are going to be different, and then that would mean that the total amount is not equal to square root of K. Like, I think I'm gonna keep reading and I'll think about that later, probably. Positions on the very small ranges act similarly to limit orders. If the range is crossed, the position flips from being composed entirely of one asset to being composed entirely of the other asset, plus accrued fees. If the range is crossed, the position... Okay, there is a limit to how narrow a position's range can be. While the price is within the range, the limit order might be partially executed. When the position has been crossed, it needs to be withdrawn. If it is not, and the price crosses back across that range, the position will be traded back, effectively reversing the trade. Yeah, so he's gonna follow an integer, and but that's just the sum of the positions. So V2 goes from 0 to infinity. Then this goes from the range. Yeah, this is very confusing. I'll put some other music here. UniswapV3 makes a number of architectural changes, some of which are necessitated by the inclusion of concentrated liquidity, some of which are independent improvements. Multiple pools per pair. In Uniswap V1 and V2, every pair of tokens corresponds to a single liquidity pool, which applies a uniform fee of 0.3% to all swaps. While this default fee theory historically worked well enough for many tokens, it is likely too high for some pools, such as pools between two stablecoins, and too low for others such as pools that include highly volatile or rarely traded tokens. Uniswap V3 introduces multiple pools for each pair of token, each with a different swap fee. All pools are created by the same factory contract. The factory contract initially allows pools to be created at 3 fee tiers. Additional fee tiers can be enabled by unique governance. Non-compounding fees. Fees earned in earlier versions were continuously deposited in the pool as liquidity. This means that liquidity in the pool would grow over time, even without explicit deposits. The fee earned is compounded. In Uniswap V3, due to the non-fungible nature of positions, this is no longer possible. Instead, fee earnings are stored separately, held as the tokens in which the fees are paid. Removal of native liquidity tokens. In Uniswap V1 and V2, the pool contract is also an ERC20 token contract whose tokens represents liquidity held in the pool. While this is convenient, it actually sits uneasily with the Uniswap V2 philosophy that anything that does not need to be in the core contract should be in the periphery, and blessing one canonical ERC20 implementation discourages the creation of improved ERC20 token wrappers. Arguably, the ERC20 token implementation should have been the periphery as a wrapper on a single liquidity position in the core contract. The changes made in Uniswap V3 force this issue by making completely fungible liquidity tokens impossible. Due to the custom liquidity provision feature, fees are now collected and held by the pool as individual tokens rather than automatically reinvested as liquidity in the pool. As a result, in V3, the pool contract does not implement the ERC20 standard. Anyone can create an ERC20 token contract in the periphery that makes a liquidity position more fungible, but we will have to have additional logic to handle the distribution of or reinvestment of collected fees. Alternatively, anyone could create a periphery contract that wraps an individual liquidity position including collected fees. And so maybe I should spend more time trying to understand the equation there, because I don't think they're gonna talk about it anymore. Thanks for the follow. I see your name. Send Cork. Yeah, this is the thing about X that I also didn't understand in the first document I was reading. I think I'm gonna spend more time trying to understand this equation here. The biggest problem is, maybe I shouldn't actually, because yeah, what I need to understand, I think, yeah, but this is already says that the rate doesn't change, so, which is the thing that I was thinking about. Because I remember the first time I saw this, I thought that the range, the equation of xy equals k would change for something else that follows an exponential curve instead of I guess this is exponential as well, but I thought the equation would be different. But I guess this is important as well to understand. But maybe not, because it doesn't affect the trading, I think. Oh, actually, it probably does. And the reason why is because the price is gonna fluctuate according to the reserves. Yeah, but only the total amount of reserves. Actually not, because if you have if you have differences in ranges, then you're gonna have a spread between orders, I think. And I think that's another question. What happens if the ranges are set up in a way that there is a spread between them and the price falls into the spread. So that would mean that the people have to adjust the liquidity. I guess it probably is not gonna happen because everyone chooses the same range pretty much, depending on the price. But what happens if there is a difference there? But I think as long as it is continuous, it doesn't affect the trading, probably. Because what changes the price is just the movement, the flow of money in and not the total amount of the reserves, I think. It's probably not that important actually to know that. But I should probably write here as well the equation for this, for the rate. Because I'm pretty sure now that it is that x times y equals k thing. Yeah, rate is I think I stop here. No fungible liquidity. I think I read this already. Yeah, probably stopped in the governance. The factory has an owner which is initially controlled by Uni token holders. The owner does not have the ability to halt the operation of any of the core contracts. As in UniswapV2, UniswapV3 has a protocol fee that can be turned on by Uni governance. UniswapV3 Uni governance has more flexibility in choosing the fraction of swap fees that go to the protocol and is able to choose any fraction. Actually, I think that's probably not really important as well, because it's not gonna, unless there is an update of course, but it's not gonna interfere with the trades as well. UniswapV3 includes the 3 significant changes to the time-weighted average price oracle that was introduced by UniswapV2. Most significantly, UniswapV3 removes the need for users of the oracles to track previous values of the accumulator externally. UniswapV2 requires users to checkpoint the accumulator value at both the beginning and end of the time period for which they wanted to compute TWAP. UniswapV3 brings the accumulator checkpoints into core, allowing external contracts to compute on-chain TWAPs over recent periods without storing checkpoints of the accumulator value. Another change is that instead of accumulating the sum of prices, allowing users to compute the arithmetic mean TWAP, UniswapV3 tracks the sum of log prices, allowing users to compute the geometric mean TWAP. Finally, UniswapV3 has a liquidity accumulator that is tracked alongside the price accumulator, which accumulates 1 divided by L for each second. This liquidity accumulator is useful for external contracts that want to implement liquidity mining on top of UniswapV3. It can also be used by other contracts to inform a decision on which of the pools corresponding to a pair will have the most reliable TWAP. As in UniswapV2, UniswapV3 tracks the running accumulator of the price at the beginning of each block multiplied by the number of seconds since the last block. A pool in UniswapV2 stores only the most recent value of this price accumulator, that is, the value as of the last block in which a swap occurred. When computing average prices in UniswapV2, it is the responsibility of the external caller to provide the previous value of the price accumulator. And I'm not sure if I'm understanding this actually, to be honest. This accumulator thing and this ticket, this tick is very confusing to me. I think, yeah, maybe I should go through UniswapV3 actually. To understand this. One for the price of token 0 in terms of token 1, and one for the price of token 1 in terms of token 0. Users can compute the time-weighted arithmetic mean of the prices over any period by subtracting the accumulator value at the beginning of the period from the accumulator at the end of the period. Then dividing the difference by the number of seconds in the period. Note that accumulators for token 0 and token 1 are tracked separately, since the time-weighted arithmetic mean price of token 0 is not equivalent to the reciprocal of the time-weighted arithmetic mean price of token 1. Using the time-weighted geometric mean price, as UniswapV3 does, avoids the need to track separate accumulators for these ratios. The geometric mean of a set of ratios is the reciprocal of the geometric mean of the reciprocals. It is also easy to implement in UniswapV3 because of its implementation of custom liquidity provision, as described in section 6. In addition, the accumulator can be stored in a smaller number of bits, since it tracks log p rather than p, and log p can represent a wide range of prices with consistent precision. Finally, there is a theoretical argument that the time-weighted geometric mean price should be a truer representation of the average price. Instead of tracking the cumulative sum of price p, UniswapV3 accumulates the cumulative sum of the current tick index. The logarithm of price for base 1 point with this number, which is precise up to 1 basis point. The accumulator at any given time is equal to the sum of log p for every second in the history of the contract. Accumulates the cumulative sum of the current tick index. So the question is, what is the tick index? We want to estimate the geometric mean time-weighted average price over any period T1 to T2. To compute this, you can look at the accumulator's value at T1 and T2, subtract the first value from the second, divide by the number of seconds elapsed, and compute the number divided by x to compute the time-weighted geometric mean price. So is the sum of all the prices from this time period. And the P is each tick which follows this, I think. Which is very close to the price. If I remember correctly, this P is the price of both tokens. Yeah, it was a little bit confusing on the other documentation as well, because I wasn't sure if it's the price of the first token or the second one, or both. I think it's, yeah. The cumulative tick was probably the price of both, given a time range. The last price minus the initial one, divided by the time range, and yeah, which is what it's saying here. Yeah, I might have to do that actually. Because it's probably... Yeah, obviously they built V3 based on V2, but... The reason why I want to do V3 is because it's the most difficult one. And because it's the most difficult, there's more opportunity, so... And I also have to study a bunch of other ones. So I'm not really sure, because that's the problem. It's because I have an idea of the things that I want to do, and I don't want to lose track of what I want to do. So for this, I think the only thing that I really wanted is the rate, and then everything else is just a bonus. And the reason why I want the rate is because I want to connect all the different DEXs and figure out the relationship between them, the price, the flow of the price. So I'm not necessarily interested in fully understanding, but yeah. Because then if I study the V2, it's probably gonna be a lot of documentation as well. It might be a waste of time or side tracking from where I want to go. And I think eventually this is the direction that things will go as well, because it's just more efficient. It doesn't make sense for people to allocate all their money and then just leave it there. It's far more efficient to have this thing here. That's why they did it this way. So I assume that people will learn this and then start using the pools that have this. Obviously it's gonna take some time, but if you want to find the opportunities, you have to be using the stuff that is most recent. Oh, really? Why would you say that? You think that the complications V3 creates don't actually end up helping as much as they thought it would initially? I never actually used them, but so far from reading this, it makes a lot of sense. Allocate capital for liquidity and try to help LPs account for IL. What is IL? I haven't seen any evidence this model actually helps most people avoid it. Oh, impermanent loss, I guess. I thought what they would do as well is change the rate from this linear equation. And I think I saw another DEX talk about this, because I don't think this curve closely resembles the supply and demand dynamics. It's probably impossible. Actually, I think it's impossible to accurately mimic the supply and demand thing to make the price differences mimic the supply and demand of normal markets, but I think this equation doesn't. It's probably gonna be more complex in the future, I think, if I had to guess. Because the way that orders get filled in normal exchanges doesn't follow this curve, I think. The x times y equals k. Yeah, but my main point of confusion is true. I think I understand the virtual thing on the concept level, but the equation is not. I kind of get it, but I'm not really sure. I think the way they explained here makes it a little bit difficult to actually understand what they mean by this. Or maybe I'm just not understanding because I didn't read the V2 thing, but so this is one, and the other one is the tick thing, which is also something that's not really clear. Like, what exactly is a tick? Is it in the same way that normal exchanges work, where you have opening and closing prices and you have difference in time between them? And that's the amount of time that it takes to build one tick is the deciding factor between the liquidity, the concentration of liquidity, or the virtual liquidity thing? Or am I understanding this in the wrong way? The academic description of these kinds of markets are constant formula, vector markets, and geometric mean market makers. In case you're interested in searching for other much more abstract generalizations of this x times y equals k concept regarding the V3 issues, I've seen a few papers like this. Oh, thank you for sharing. I'm definitely interested. My only problem is time, because there's so much thing to study, so I'm not gonna sure if I'm gonna study this, but that compares the potential impermanent loss between V2 and V3, and V3 never seemed much better to me personally. I think you have a good high level idea of the concepts, but I'm not an expert either. I misunderstood what you mean. Yeah, of course. Yeah, it's definitely, not definitely, but I strongly believe that it is impossible to find an equation that is going to be perfect, because supply and demand is unpredictable, and because it depends on the context, the circumstance. Markets are decentralized computations, so they is pretty much a response to the environment. And because you can't predict the future, it's impossible to find an equation that is gonna predict the supply and demand of different coins. So there's always gonna be these discrepancies, and that's why they made it so that people could arbitrage off this in order to reach equilibrium. But I think the window for that is probably small, because the problem is, obviously, the more time goes on, data becomes more important, and then whoever has access to the most data puts machine learning algorithms and gains on. But the thing is, on the other side, the blocks have a limited time, so you can't really win on speed, I think. My main criticism of V3 boils down that the code is much more complicated than V2. Yeah. But don't you think that eventually it's gonna get more complicated anyway? Like, I'm not saying that they are the best, but it's probably gonna be more complicated, so. Yeah, but you can't really change the... Well, you can change the size of the block, I think. Yeah, on Ethereum you can change the size of the block, but there are limits, right? And you're always depending on the mempool. So it's different than the normal exchanges and the normal forex trading, for example, where the fastest one always wins. For pricing and market data. Yeah, hopefully it reaches an equilibrium between centralized and decentralized. But it's just the issue to me is that it's not necessarily that the problem is in cryptocurrency. It's just that it is following the same rules that the market economy follows. So eventually it's gonna be centralized because regulations are part of the incentive system. So the natural progression is always to polarize and is gonna be following the Pareto distribution. So, and I think as long as it follows a market economy, it's gonna be... It might take a long time, but it's gonna eventually end up being like that. And I don't know how, but I think that's what's gonna be happening. I agree that things should be more complicated. Let's learn more and make better models, but I think this complication is to bring benefits, should be... If it's better otherwise. Yeah, I agree with you. But I think that's the normal progression. So what's probably gonna happen is it's gonna get more complicated. Then people find ways to simplify, and then it goes like a wave. Uniswap definitely has the feeling of first mover advantage that it ends up making a suboptimal solution very popular. Exactly. And usually the first mover is not the one that succeeds. It's usually the ones that learn from the mistakes and then... But yeah, we'll see, I guess. I guess my main interest is not... And the problem is the equations are a part of it. But I want to understand or create a model of how the money flows. I think the equations are important for that. Because they are like the gates that regulate the water. So you have the flow of money between exchanges, both centralized and decentralized, and then the difference is that on decentralized exchanges, because it's an equation, it's more predictable what's gonna happen if you understand the flow of money, the volume in and out. And I think in markets, normal markets is different because you can't predict the impact. But I'm not really sure about that. And I guess the reserves are important as well because of that, because yeah, they determine the liquidity. In addition to the seconds weighted accumulator of log price, UniswapV3 also tracks the seconds weighted accumulator of 1 divided by L, the reciprocal of the virtual liquidity currently in range at the beginning of each block, seconds per liquid cumulative. This can be used by external liquidity mining contracts to fairly allocate rewards. If an external contract wants to distribute the rewards at an even rate of R tokens per second to all active liquidity in the contract, and a position with L liquidity was active from T0 to T1, then its rewards for that period would be R times L times this thing here. In order to extend this so that concentrated liquidity is rewarded only when it is in range, UniswapV3 stores a computed checkpoint based on this value every time a tick is crossed, as described in section 6.3. This accumulator can also be used by on-chain contracts to make their oracle stronger, such as by evaluating which fee tier pool to use the oracle from. In UniswapV3, each pool contract tracks the pool's current reserves, X and Y. The contract could be thought of as having virtual reserves, values for X and Y, that allow you to describe the contract's behavior between two adjacent ticks, as if it followed the constant product formula. Instead of tracking those virtual reserves, however, the pool contract tracks two different values, liquidity L and square root price. This could be computed from the virtual reserves with the following formula. So L is equal to square root of X times Y. And the price is the inverse. Yeah. Conversely, these values could be used to compute the virtual reserves. Using L and square root of P is convenient because only one of them changes at a time. Price and thus P square root of P changes when swapping within a tick. Liquidity changes when crossing a tick, or when minting or burning liquidity. This avoids some routing errors that could be encountered if tracking virtual reserves. We notice that the formula for liquidity based on virtual reserves is similar to the formula used to initialize the quantity of liquidity tokens based on actual reserves in UniswapV3 before any fees have been earned in some ways. In some ways, liquidity can be thought of as virtual liquidity tokens. Alternatively, liquidity can be thought of as the amount that token 1 reserves, either actual or virtual changes for a given change in the square root of price. So I think that one might help me understand the equation up there. So here L equals K, which is the liquidity. So it doesn't track the virtual reserves. So price of y is equal to price times x, but it's not equal k, it's equal the square root of k. Yeah, I think I'm gonna have to read this a bunch of times, or maybe I should just move on to the other ones as well. I also have this paper here to read. And so maybe this one will help me understand the other one. Constant product market is a market for trading coins of type alpha for coins of type beta, and vice versa. This market has reserves are alpha bigger than 0, or constant product k equals r times r, and percentage fee 1 minus omega, whatever this is. No, it's not omega, I don't know how to say this, but whatever. Transaction in this market, trading coins B for coins A, must satisfy R minus. So R is the reserve and delta is the difference. After each transaction, the reserves are updated in the following way. Yeah, so I'm gonna spend some time trying to understand this one as well. Yeah, so I think delta alpha is the same as delta B plus times the fee. So it's gonna decrease in R, the reserves are gonna decrease in R with the same proportion that are gonna increase in B times the fee. That's what this is saying, I think. And K equals this. We always require that R alpha, RB bigger than 0, such that any trade that results in a non-positive reserve is never fulfilled. We say that such a trade has infinite costs. Okay. The name constant product market comes from the fact that when the fee is 0, this letter equals 1, any trade delta beta to delta alpha must change the reserves in such a way that the product remains equal to the constant. In this section, we derive bounds on the marginal price of the market relative to a reference market and show that this market maker has other desirable properties. In the optimal arbitrage problem, we have two coins, alpha and beta, which we can trade either with a reference market or a Uniswap contract. In this problem, we seek to maximize the profit made from trading, say, some amount of loaned coin alpha beta of coin beta to some amount of delta alpha of coin alpha via the Uniswap market. We then trade back to receive the received alpha delta alpha for delta beta and pay back the loan to receive profit. If our profit is positive, that is, if greater than 0, then we say that there is an arbitrage opportunity, since we have made money for free, by only trading coins within different markets, without taking on any risk. The optimal arbitrage problem then asks, what is the maximum profit that can be made by this scheme? In the infinitely liquid market case, in the case that delta beta this thing equals MP times delta, where MP is the reference market price of coin alpha, which is gonna be the factor that provides the profit to the amount that they are different. You can phrase the optimal arbitrage problem as the following optimization problem: maximize subject to. Yeah, I'm gonna have to go slow on this one. So, pretty much the same that is written here. And both of them are bigger than 0. And this equation is just the equation of the differences on the trade, I think. We have optimization variables constraint to be non-negative. Here is the Uniswap exchange fee. And the constraint is the definition of constant product market. When written in this form, problem 2 is not obviously convex, though we show in Appendix A that it can easily be written in a convex form and then derive an analytical form for the optimal trade amounts. No arbitrage conditions. Assuming that the no arbitrage condition is satisfied, which often approximately holds in practice, we can show that the Uniswap market price deviates from the market price by at most a factor of y. Oh, so pretty much it's saying that if the factor is not bigger than y, then it means that there are no arbitrage. In a very complicated way. The marginal price of a coin alpha in Uniswap is defined as the price of an infinitesimally small trade. This price can be found by differentiating the constant product market formula. So taking the derivative of the product and it gives this formula. Yeah, so I guess you can just do the product and then the constants get to 0 and solve the other derivatives. and pass this one to the other side. I just don't understand what's MU here. I have written MU equals RB divided by RA for the Uniswap price of coin alpha VTF. You can always make a non-zero profit if the Uniswap marginal price of alpha y divided by -1 MU is smaller than the market marginal price MP. By performing a small enough trade, assuming there is no arbitrage, this means you must have MU bigger or equal to this. So MU is the minimum amount to break even. Similarly, by swapping alpha for beta and combining the resulting statements, we get the following bounds on the Uniswap market price relative to the true market price. I'm probably gonna have to take a break soon, I think, because I'm already really tired. Assuming no arbitrage conditions, this suggests that in practice, the larger the trade fees are, the larger the gap between the true market price and the Uniswap market price may be. Of course. For example, in the case that the trade fee is small, bound 3 is approximately equivalent, sure. So obviously, the bigger the fee, the more discrepancy of prices in order to compensate. While we derived these conditions using a simple argument, we can also easily derive them by analyzing problem 2 and noting that its optimal value is non-zero if and only if there is an arbitrage opportunity. I'm just trying to see, I don't want to get lost in the letters here. So MP is market price, MU is the ratio, which is K. And because it cancels out here. And so it's pretty much saying that... Oh, but actually... Yeah, if you make the derivative taking into account these changes, when the trade approaches 0, then MU equals K, I think. Yeah, which makes a lot of sense. And then the larger the trade is, then K increases, or MU increases. Probably, not sure. Yeah, it has to be. Because then RB is gonna get bigger and bigger. Yeah, the limit is for profitable is at least paying the fee. The difference has to at least pay the fee. And this is the fee. So fee times market price has to be, if it is smaller than the MU, it doesn't compensate, I think. Yeah, because the derivative is equal to the constant there. So there is no difference between the K of the market and the K of the Uniswap. Extensions of the optimal arbitrage problem. There are several natural extensions to the optimal problem, which attain most of its useful properties. Risk models. There are many factors which could potentially cause an agent to fail to close an arbitrage opportunity, including noise information, front running, and delay in trades. The latter of which is quite common in distributed platforms. In particular, it may not be desirable for an agent to perform a trade with the exact solution of problem 2. Yeah, I don't think it's worth it to put those equations into code format. I think the last one is the one that I'm gonna probably translate. But definitely have to understand the progression, otherwise I'm gonna get lost when it comes to the end. In this case, we can add an additional term penalizing large trades. In other words, we can assign some cost of risk which can be a convex function, which is non-decreasing in its second argument. This gives a problem of the form. Maximize subject to So it's taking the difference, market price times the difference in A minus the difference in B, minus the function. And this is just stuff in the beginning. It should be noted that problem 4 can be written in a convex way and is the problem we use to simulate arbitrage in our agent simulation. One example of a risk function f could be a model of the resulting changes in the market price due to the arbitrage trade. A common and simple model for the marginal market price after a trade of size is that the resulting price is this. So the trade is size delta alpha. I don't know what this means. Any n bigger than 0, epsilon bigger than 0. The resulting risk function dt is convex. So the function is the integer from 0 to the trading, to the volume, I think. And market price minus mt. Yeah, I just don't understand what this is, but I guess. And maybe they'll talk about it later. This model, unlike in problem 4, an arbitrage is not guaranteed to reach the non-arbitrage condition in a single round if the penalty function does not reflect a true underlying market movement. Other conditions. In this section, we show a few basic and useful properties which Uniswap and other constant product markets satisfy. Increasing product constant. For every trade, the product constant K is non-decreasing and strictly increasing if this is true. That's this. And the constant product at trade T. If trade T plus 1 sells delta B coins B for delta A coins A, we have by definition so this is the equation before. It's less or equal than this new RT. For every trade, the product constant K is non-decreasing, strictly increasing. So if I is smaller than 1, means that the fee is smaller than 1, but I'm not sure if I understand. And the constant product it's the okay, so alpha and beta are the reserves and KT is the constant product at time T. If trade T plus 1 sells delta B coins B for delta A coins A, by definition. I think I understand now, but so it's saying that the K is bigger on S in the subsequent thing. Where inequality always holds strictly except when this equals 1. So if it's smaller than 1, I have that always, okay. So if the fee is less than 1, the KT plus 1 is going to be bigger. I'm not sure if I really understand this. I think I'm going to take a break actually. Because it's probably going to be better to come back to this rested. Yeah, I'm gonna take a break, then probably next time I'm gonna continue reading this from where I stopped. See if I really understand, and I'm probably gonna study the other exchanges off stream. Yeah, so see you.